Okay, so in lesson number 2, we're talking about neutralization reactions, and this is going to end up being a little bit of math. Okay, all of the math that you're going to be asked to do in this particular lesson is math that you've done before, but we're going to be doing it in small chunks. So neutralization reactions, we talked a little bit about them yesterday. We said that when an acid will neutralize a base or something to that effect when we talk about the properties of acids. So when we talk about the properties of acids, I want to take a second to actually refresh your memory as to what that means. So if we have an acid, something like HCl, and we react it with something like sodium hydroxide, which is a base. Okay. This is going to be on paper, this will be a double replacement reaction. So you'll get something that looks like this. You'll get something like H, and we talked about this a little bit yesterday. You'll make water, but I'm going to write it as HOH. And then you'll get Na, and you'll get Cl. Okay, so when we work with acids in the lab, the state of matter of the acids in the lab is going to be aqueous. And we work with bases in the lab, in a neutralization reaction, they will also be aqueous. We have to recall that the pH of an acid is going to be less than 7, and the pH of a base is going to be greater. That's not what I wanted. Greater than 7. Now you're going to produce water, and you're going to produce NaCl. So water, its state of matter in this case is going to actually be pure water, and NaCl is going to be aqueous. Now, the pH, if we have pure water, the pH will be equal to 7. Okay, and that's where we get the neutralization part. And then the other thing that you're going to get as a product here is going to be an ionic compound, or a salt. Okay. Now, an ionic compound or a salt, that kind of means the same thing. Basically, if we have a metal pairing up with a nonmetal in chemistry, we define that whole thing as a salt. This salt happens to be sodium chloride, but which is table salt, which is what the salt that most of us are familiar with. But when we balance this, we get something like that. So this is an example of a neutralization reaction where I take an acid, something with a pH of less than 7, and I mix it with a base, something with a pH of greater than 7, and I get water, pure water as a liquid, which has a pH of 7, and then I get some other product, which in this case is going to be an ionic salt. Now, there are some things that we can track or do as a result of all neutralization reactions. And one of the things that we're going to talk about is the fact that when we do work with neutralization reactions, one of the things that we should always start with is a balanced chemical equation. So that's pretty simple. In this class, you'll be provided the balanced chemical equation. The next thing is asking us to calculate the molarity, or using the molarity equation to solve for moles. So molarity, you might recall, is equal to moles over liters. And then the next step of this is we are going to use stoichiometry to go from moles to moles. So it might be moles of acid to moles of base, or it might be moles of base to moles of acid, but we're going to be going moles to moles basically. And when we do that, we will need the balanced equation. And then we will use the molarity calculation a second time for our final answer, which will be moles again over liters. Okay, so regardless of what the problem gives us, in all of the problems that you're going to be working with, it's going to be a 3-step approach. You're going to be using the molarity formula to solve for moles. You're going to be using some form of stoichiometry to convert maybe moles of acid to moles of base, or moles of base to moles of acid. And then you're going to use the molarity equation to get your final answer. So it's going to be 3 steps. Now, before we go super far into this, I want to take a second and I want to ask the group here as a whole, like, if I'm looking at a chemical compound or a chemical formula like KOH or H2CO3, I can tell which one is the base. Can anybody tell me what it appears, based on the knowledge that you have from yesterday, that bases have in common in terms of their chemical formula? What do they all have in them? Pardon? Close. He said H. Close. He said HO. And the reality is yes, you are right, that bases have OH in them. Okay? So if I'm looking at my problem here, I can see that I have some information about a base because it's KOH, and I see that this OH right here is telling me something, that a base is present. Now, the other part is an acid, and acids tend to have hydrogen at the front. So in this problem, I see that there is H2CO3. So I see that there is H at the front. So that leads me to believe that I have an acid. That is not 1000% always the case, but for the scope of this class and when we do neutralization reactions, that will be the case. Now, looking at this problem here, I see that I'm asked to calculate the volume of 0.5 molar KOH solution needed to completely neutralize 0.00750 liters of a 0.125 molar solution of H2CO3. Now I've got this 0.0750 liters hanging around out here. What does that seem like it belongs with based on how the problem is worded? Is that 0.0750 relating to the base KOH, or is it relating to the acid H2CO3? So the 0.0750 liters, does that look like it belongs to the base, the KOH, or the acid H2CO3? Yeah, this actually belongs to the H2CO3. So I've got some information about a base, and I've got more information about an acid. So the way that I'm going to work out this problem, again, working through the 3 steps. The step 1, is going to be to calculate the moles, and in this case, it's going to be of acid. So we're going to calculate moles of acid. And when we do that, based on our steps to solve up above, we're going to start by using the molarity equation. So I'm going to go ahead and identify my variables. I have molarity, I have moles, and I have volume. And in this problem, I see that the molarity of the acid is 0.125. And the volume of the acid is 0.0750 liters. So I'm going to plug that into my molarity formula. Which is moles divided by liters. And when I plug that in, I'm going to take the 0.125 molar H2CO3. I'm solving for moles. And I'm going to take the 0.0750 liters. Now I'm solving for moles, and as we did in the past, we multiplied both sides by 0.0750. So 0.0750 liters times 0.125 molar will give me moles. So I'm going to grab my calculator. I'm going to take 0.0750 times 0.125, and the calculator is going to give me a value of 0.009375 moles of H2CO3. So this looks like it's a really tiny number, and sometimes students get a little freaked out by that. But in reality, that number is right where you want it to be. So that's our first step complete. Step 2 is we are going to convert, in this case, moles of acid to moles of base. Hang on. So in step 2, we are converting moles of acid to moles of base. Is that what your question was? Okay. So in order to do that, we're going to go mole acid to mole of base. So we're going mole to mole, basically. So I'm going to take the value that I just calculated, which is the 0.009375 moles of, in this case, it's H2CO3. Put it over 1. And when I go mole to mole of something, what do I need to know, find, or calculate? Do you remember? So when I use stoichiometry and I go moles to moles, what do I need to know, find, or calculate? Not the molar mass, but moles in it. You got the right idea. So if we went moles to mass, we use the molar mass. If we went mole to mole, what do we need to use? Pardon? Molarity, not quite. We're almost there. We would use our mole ratio, right? And our mole ratio comes from our balanced chemical equation. So I've got moles of KOH and moles of H2CO3. So when I identify my ratio, I'm going to say that I have 1 mole of H2CO3 for every, looks like 2 moles of KOH. So in this problem, I'm going to set it up so moles of H2CO3 cancel out. So I'm going to put the 1 mole of H2CO3 on the bottom. And 2 moles of KOH on the top. Bless you. And so when I solve this out, I'm going to take my 0.009375 times 2 divided by 1, and I'm going to get a value of 0.01875 moles of KOH. So that's our second step complete. So now, yes.
How do you find the mole ratio?
I used the balanced chemical equation and I compared the two things that were given to me in the problem. The two things that were given to me in the problem were KOH and were H2CO3. So I looked at the balanced chemical equation and I saw that there was one H2CO3 and two KOHs. So that's where I got my mole ratio from. Helpful?
That's always going to be like that?
You will always get your mole ratio from the balanced chemical equation, yes.
All right.
Okay. And then the last step here is we are going to calculate, oops, if I can spell, what did I say? You're going to calculate the, volume, sorry. Of KOH. Because that's what this problem is asking us to solve for. And when I do that, I'm going to use the molarity formula one more time. Molarity, moles, and volume. This time, we were given the molarity of KOH up at the top, so that's going to be 0.500 molar. We just calculated the molarity of it in step 2. And we are solving for volume in this case. So I'm going to set my problem up where I'm going to use my formula. Molarity is equal to moles over liters. I know my molarity is 0.500 molar. I know the number of moles is 0.0187 moles, and I'm solving for a volume of liters. When I do this problem, I need to move the liters out of the bottom. So I'm going to multiply both sides by liters first. And then I'm going to divide both sides by 0.5. And that will leave me with a value which will be in liters. So I'm going to take the 0.01875 divided by 0.500. And the value that I will get for my answer here will be 0.0375 liters. So this is our final answer in this problem. Okay. And it's all of the problems in your homework today are going to be 3 steps. You're going to do a molarity calculation step, a mole conversion calculation step, and another molarity calculation step. So before we jump into the next one, which is clearly going to be a U-try, okay, let's take a second and identify what we're working with here. And just to refresh your memory, bases would have OH in them, and acids would have hydrogen at the front. Now, can someone tell me, reading the problem, what the base is? Yes, in this case, the base is the 0.250 liters of a CaOH2 solution. And that would mean that our acid in this problem is going to be 0.0650 of a 0.100 molar HCl solution. So this is absolutely going to be a you try situation. So I'm going to give you some time to work on that right now, and then we'll come back and regroup. So go ahead and calculate the, in this case, molarity of the base. Okay, many of you have gotten to the point where you're done or almost done with this problem. And those of you that I was able to come around and check, either I got you like on the right track, back on the right track, or you had it right. So let's take a look at the work that I did. In this case, you were given information about the acid. So you're given the volume and the concentration of the acid. So I used that to solve for moles of acid in my first step. So I calculated moles of acid. In the second step, I went and I took that moles of hydrochloric acid and converted it to moles of base, CaOH2. So when I did that, I got 0.00325 moles of calcium hydroxide, CaOH2. And from there, the problem actually asked me to simply calculate the molarity, big M, of the base, the CaOH2. So in this case, I just plugged in the moles of the base that I just calculated and the volume of the base that I was given. And I got the molarity to be 0.130, appropriate number sig figs, molar CaOH2. Okay. So, um, so that's how we're going to attack these problems. There'll always be a molarity calculation with a mole conversion stoichiometry calculation with another molarity calculation at the end. So you have some practice tonight to work on that. So go ahead and use the rest of the hour for that.